good day, everybody, and welcome to the professors from McMurray University. I'm Paul Fabrizio.
I'm Don Frazier, and once again we have Wayne Keith, another professor.
I'm back. That's right. He's back
from
for
McMurray
more.
University.
He's a glutton for punishment, something like that.
But he's also
I'm
talking,
still having fun.
yeah, physicsy stuff too. Takes some time.
And it elevates our IQ
Yes.
to have him here.
It does.
So this is really good. Now, Wayne Keith
Mm-hmm.
is a professor of science, space physics, right?
Space physics.
That's what we decided last week.
Space physics.
And last week he was talking about dark matter.
Mm-hmm.
And today we're going to talk about dark energy.
Which is even more weird.
Which is even more weird. But just as a recap, dark matter is something that we cannot see, but we know exists because it has mass. And anywhere from 60 to 90% of the universe is filled with this black void.
Yeah.
But you can measure it.
We can feel its
can
gravity. We
you
can
can-
measure its gravity, but we can't see it directly. We
But
can only see its effect on things.
Even calling it black void though is a construct.
You're right.
Yeah, so
So
it's
we're going to struggle with the limits of our vocabulary
Yeah.
today when we talk about dark energy.
yeah.
Okay?
Right.
Okay, now I hope everybody's ready.
Yeah,
You
strap
gotta
in.
buckle
This
up
is
for
going to
this
be full contact today.
Anyway, so dark energy, where do we start? What are we talking about? Why are we here?
Well, I struggled with this one trying to figure out where to start this scenario, but there's a couple of ways we can start. One is there was a problem with our understanding of the universe back in the 1980s, where we were pretty sure we understood how much density the universe should have. So that's mass per volume that the universe should have. If it has a certain amount of density, we call it the critical density.
Okay.
Okay.
And so if it has the critical density, then we say the universe has a flat geometry. And I'm not going to try to go any
Okay,
deeper
we're
than
just
that.
going to accept that, right?
But
We're
in
gonna-
essence, we're trying to measure the corners of the universe and
in
figure
a
out
sense, yeah.
kind of what all's in
If
it, what's the inventory list, and all
If
that.
it has
So
more
that's-
than that density, we say it's a closed universe. If it has less than that density, we say it's an open universe. If it has exactly this critical density, we say it's a flat universe. The universe has a flat geometry is what a lot of times it's stated.
Okay,
Okay.
so we're just going to accept this.
We're going to accept
So
it.
this
There are
was in the-
observational reasons to think that the universe is flat.
And this was in the 1980s. So we're
Yeah,
not talking
up to-
100 years
right.
ago. We're talking 30
Up
years ago.
to the 1980s.
I was in high school. I didn't understand my universe at all then. So
This was the
Do
thing.
you now? No.
Now
it's pretty flat.
the problem with this idea was that we say, okay, well, if the universe has a certain density, let's measure, right? What how much stuff do we see? And so we find all the regular matter we can, and that's not enough. That's about 5% of what we need to get to the critical density.
So it's
then,
not
okay. We add dark matter, right?
All right.
We add dark matter. Okay, great. That's
now we get to that number.
that's another 25%.
What?
Oh wait.
Remember, because it's about 90-10, but still 5%, 25%. We're only 30% of the way to the critical density that
Of what we think this should
what
be.
we think should be there. And so this was sort of a nagging, ongoing problem in cosmology, in the study of the universe through the 80s and 90s, that we think the universe should have the critical density, but like, where's the other 70% of anything?
So you can't account for 70%?
Yeah, that's
So
of the
why don't you
universe?
just say,
Problem.
well, we'll call it good, and we now have an open universe.
Yeah.
yeah. Well, there's observational reasons that we think that it's flat.
That's not that
Yeah,
way.
you look
Okay.
at the very distant universe. There's sort of a background glow to the whole universe. We can see in every direction. It's called the cosmic microwave background radiation. It's a fun name, and you
Okay.
can think of it as the sort of afterglow of the Big Bang that we see in all directions. And we can measure that in detail and see little fluctuations and stuff in that background, and different computer models for how the early universe worked give different predictions for how big these fluctuations should be, and the fluctuations match what we expect for a flat universe. So that's just one of several
Okay.
lines of evidence that the
So
universe should be flat, but we just don't know where most of the stuff is.
Now, before we get too far down that road, by flat, are we talking about like
A piece of paper
flat,
flat?
piece of paper flat?
Yeah, sort of.
So
So-
if we could visualize it, you're arguing that the universe
Is a
doesn't have an
disk?
up or a bottom. It
Well,
just
we're just saying that, like, if you just measure space as, like, two-dimensional plane, we think of it, that it's flat. It's not
Okay.
curved upwards or downwards.
okay. Is there
It's hard to explain.
is there depth to that flatness?
Yeah, well, normally when we talk about that sort of stuff, we reduce the universe to 2 dimensions so we can visualize it.
Yeah.
Okay.
But it's actually 3 dimensions. But it's hard to visualize being flat.
So
in
it can be flat, but
three-dimensional.
can also be pretty thick.
yeah. There you go. Okay.
Yeah,
So, but you're
So-
missing 70% of it.
missing 70%. So separately from that, we had some ideas about what we thought how we thought the universe should. The expansion should change over time, because we've known since the 1920s and into the 30s that the universe was expanding. That everything's getting further away from everything else
Okay.
at large distances, and that's what led to the idea of the Big Bang. That if everything's getting farther apart from everything else,
There must have been a point of singularity.
yeah, then you have just run the clock backwards, and everything's getting closer together. And so that
Singular.
I said a sciencey word.
those ideas date back to the 1920s and 30s. So if the universe is expanding, gravity, because all these things have mass, right? The regular matter and the dark matter all has mass, and it should all be pulling back on itself, right? Because it's mass. Gravity wants to pull things together, and so it was expected that the universe would decelerate over time. That the early universe would have expanded faster, and then as time goes by,
it would collapse.
it wouldn't. Well,
It
if
would
we had a
start to
closed
come-
universe, it would collapse.
Okay, but it would start to
With
come back.
the critical density, it would not collapse. It would just slow to a stop, but never,
Oh.
And everything be in its place.
pretty much.
Okay.
But it would take forever for it to come to a stop. So it would basically expand forever, but just keep
Okay.
slower and slower and slower.
Okay.
And so in the mid to late 90s, so I'm talking fairly recent. I was already in graduate school, by 95. So in the mid to late 90s, they
we
were
were here
Yeah,
working
he's a mere pup.
So
in the mid to late 90s.
mid to late 90s, there was astronomers that were looking at supernovas. It's a certain type of supernova called a type 1A supernova. I told you there was going to be a lot of background.
Yes.
And what's special about a type 1 supernova, this is a
Type 1 or Type 1A?
it's a type 1A. Type 1 is different. Well, there's type 1A and type 1B.
Okay.
So this is a type 1A. And what's special about a type 1A supernova, this is a star that's blowing up. They always explode the same intrinsic brightness.
Okay.
Because it's a particular type of star that's the core of a dead star like the sun. After the sun dies, its core will become a white dwarf.
Okay.
And so if a white dwarf, the way that a white dwarf explodes is by gaining too much mass, either by stealing it from another star or your binary companion or something. And once it reaches 1.44 times the mass of the sun today, we call that solar masses, 1.44 solar masses, then it collapses and explodes as basically a thermonuclear bomb because it's made out of
Okay.
carbon. So they always blow up at the same brightness intrinsically. So if you measure how bright it appears to be, you can tell how far away it is
Okay.
because
makes
light gets
sense.
dimmer with distance.
Okay.
Right.
And so we call in astronomy they call that a standard candle. It's something that you know how bright it really is, and so if you measure how bright it appears to be, you can tell how far away it is.
Okay.
Perfect.
That
All right,
makes
I
And
got
sense.
so and these things are bright enough that you can see them when a supernova goes off in a very distant galaxy, billions of light years away. You can still see it happen.
And you call it the Christmas star.
There you go.
Okay.
Well, if it's that far away, you have to have a pretty good telescope to see it.
Okay.
So
Christmas star.
I'm just trying to, I'm
what-
trying to sink
well,
my hooks into this.
to give you a point of comparison, if a supernova goes off in our galaxy, it would be bright enough to see in the daytime.
Okay.
Anywhere in our galaxy,
Anywhere in the Milky Way.
anywhere in the Milky
it'd
Way,
be
we would be bright
to
enough to see it in the daytime.
And
That would be the
the-
Christmas
the
star.
star. Yeah.
If it
okay.
happened within 50 light years, it would actually damage the Earth's atmosphere. So, but there's
So
not any in
there's no
there's not
star.
any within 50 light years.
Okay, so we're
Phew.
good.
maybe it's 50 parsecs. I can't remember now.
Okay.
Which is about 150 light years.
Okay, we got a minute, a little bit
Okay,
more than a minute.
So let me finish talking about type 1A supernovas.
Okay.
So astronomers looked at these very, very distant type 1A supernovas. We know how bright they're supposed to be. We see how bright they are, and we can measure their distance. And the idea was to measure the deceleration of the universe.
Okay.
You see how fast the universe was expanding back then compared to how fast we know it's expanding now, and you can see that deceleration because of gravity.
Okay, so
that
something happened.
When they did it, they found that the universe is not, in fact, decelerating. It's accelerating. This is completely unexpected.
Wow.
Is that been verified, checked again and again and again?
That was announced in 1997.
Said the political scientist. Have you checked your math on that?
So in the last 20 years, since 1997, everybody's been studying this.
Everybody's on the same page. So in 21 years ago, we discovered that the universe is still expanding.
And it's accelerating.
And it's
getting faster and
faster.
Faster and faster, which was totally unexpected.
Okay, we've got to stop in 12 seconds.
Unlike the universe.
Yeah,
Right.
which apparently doesn't stop.
No.
So I guess this means we're still at the beginning of the Big Bang, right?
In a sense, I mean, the universe is getting
All
bigger.
right, we'll talk about it after this break.
Don't skip! Don't skip! Don't skip!
Hello, my name is Christopher Bartlett. I'm the studio manager with the McWhinney History Education Group, and you may be used to seeing my name in the end credits, or sometimes you'll see me sitting here as a special guest host. But right now, I'm here to talk to you about an amazing new opportunity. We have created a Patreon. To put it simply, if you enjoy the content on this YouTube channel, then you can head on over to Patreon, donate money to us, and become a patron. And through your donations, more content will be made. Basically, it breaks down like this. With $10, you will receive a short thank you video from Dr. Frazier and Dr. Fabrizio. With $25, you will be able to take part in a patron-only poll. With $50, you will get swag. These items include a choice between 2 prints of paintings and signed copies of Dr. Frazier's books, Blood on the Bayou and Thunder Across the Swamp. With $75, you will receive exclusive videos that will not be available anywhere else, not on YouTube and not on SoundCloud. These videos will be just for you, the patrons. With $100, your name will appear in the credits. See that right there? That's where your name can be. Finally, for $500, we will send you a signed collector's edition of Phil Collins' book, The Alamo and Beyond. Yes, it is signed by Phil Collins himself. And remember, for all the higher donations you do, you also get the stuff from the lower ones as well. So it's pretty cool. And when we reach our goal of $5,000, Dr. Frazier and Dr. Fabrizio will give you their own personal ranking of the presidents from worst to best. Coming from the perspective of a historian like Dr. Frazier and a political science expert like Dr. Fabrizio, you really don't want to miss their ranking and why they put them in that order. If you enjoy this content and want to see more, if you believe in our mission of making history accessible to everyone, then head on over to our Patreon and donate as much money as you're willing to give. You'll help us continue what we're doing, and you'll get amazing gifts as our way of saying thank you. Now we return to your regularly scheduled programming.
And we're back, and this is Paul Fabrizio.
I'm Don Frazier, and we're joined by Wayne Keith, a
Space physicist.
That's right. I was going to throw astronomy in there
Oh.
too, but no,
Oh,
it's
no.
space physics.
That's right.
We need a cape, dude. All right.
And a uniform, but we won't,
And a uniform.
we won't go there.
And
All
you
right.
can announce the Christmas star.
That's right.
Apparently, you thought that was ridiculous.
I did.
I think
I enjoyed
we
it.
talked on the radio once about the Christmas star one Christmas, a long time ago.
I think we
I think
did.
we did.
Yes.
And it was a supernova.
Different.
It was
well,
a
that was
supernova.
one of the possibilities.
Was it a type 1A or a type 1B?
Well, it could have been either.
Okay.
We just don't know.
We just
It
don't
could
know.
have been a
'cause I
type
don't-
2 supernova.
I don't even
Those
know what
two.
these are yet because he's going to tell us.
Yes, he is. So we're trying to get to the mystery of dark energy.
Right.
And where you've left us is that about 70% of the universe is unexplainable,
Right.
and that 21 years ago, you folks discovered that the universe is expanding and accelerating.
The universe, the expansion
which
is
not what
accelerating,
you
which is
expected.
not what they expected. They expected to measure a deceleration. They measured an acceleration, which obviously everybody had to go back to the drawing board to figure out what the heck's going on. And basically, we still don't know. but they had to give this idea, because you have to, in order for the expansion to accelerate, you have to have something pushing, right? Because gravity is trying to make you decelerate.
Yeah.
So you have to have, basically, you can think of it as a negative pressure that's pushing everything apart.
Just like an explosion.
A negative gravity, if you will, anti-gravity that's pushing everything apart. And so they said, okay, let's assume that this is uniform throughout the universe. And the reason that's a good estimate for now, we don't know for sure if that's true, but the reason we think that might be true is because at relatively close distances, and by relatively close, I mean like us to like a neighboring galaxy, like the Andromeda galaxy, it's only a few million light years away instead of billions of light years away.
Yeah. Oftentimes get their mail delivered to us.
Exactly. So it's sort of
weird.
Our neighborhood, as the universe goes. We don't see any evidence of this dark energy. We don't see any evidence of this acceleration pushing things apart. But at what we call cosmological scales, really, really far distances, billions of light years across the universe, then we see that it's actually stronger than gravity. That's why there's an acceleration and not just a slower deceleration than we might have thought. It's an acceleration because once you get to big distances, gravity gets weaker and weaker and weaker. But this, whatever it is, it doesn't get weaker.
So there's something out there that's pushing everything away from everything else.
Right.
And it's getting stronger the farther away you are.
Well, it's not so much that it's getting stronger, but it's not getting weaker.
It's not getting
Everything
weaker.
else gets weaker as it gets farther apart. Gravity gets weaker the farther apart you get. This, whatever it is, doesn't get weaker. And so it becomes more dominant because, if this is gravity and this is dark energy, gravity gets weaker and weaker and weaker, and dark energy doesn't. Eventually, dark energy dominates, even though it hasn't gotten stronger. It's gotten stronger relative.
It's the baseline.
Yeah.
It's the baseline, and gravity's falling below that baseline. Okay.
So you know that there's something that's driving this, and you folks just decided to call it dark energy.
Basically.
So there's an energy out there. You don't know what it is. And so searching for a name, you said, hey, dark energy.
It was actually kind of following the pattern of dark matter.
Yeah.
Yeah. So dark matter, we know it's matter because it has gravity, but we can't see it, so it's dark. Here we can't see it or
even measure it
or anything, but we know it's there because something has to be driving this acceleration. And so we call it dark energy.
Now, how come it can't be just the results of the Big Bang blowing things apart? I mean, wouldn't it?
It's almost like you insulted him.
I guess so.
How dare you say that?
I'm just, if the Big Bang happened,
right,
everything blew apart, and why can't it just continue and accelerate? Doesn't fit with the?
Not really. The Big Bang, you really shouldn't think of it as like an explosion in space, like you have a bomb that goes off and it's an explosion in space. The Big Bang is really an expansion of space. Because there was no space for it to expand into. It is the universe. Whatever
it was.
It was. I mean, well, every atom in this room was present at the Big Bang. The quarks that make us all up was present at the Big Bang.
So there wasn't anything outside.
Right.
So it was like everything was like in a balloon or something like that,
so,
and then it just expanded.
Yeah, we think of it as just this, this expansion from a singularity, from a point, but it's really hard to wrap your brain around because what was it expanding into? Because there wasn't anything before it, at least not that we know of.
So it must have displaced something.
Well, but what is that?
What is it? I mean, so if you put a rubber ducky in a bathtub, it's displacing water.
Correct.
Mm-hmm.
Okay, so maybe the Big Bang
is
displacing something, and that something may be related to.
But if it was displacing something, you think that would slow it down even more, though, right?
Unless that something it's displacing is anti-gravity, and then it's dark matter. I just solved this. We can go get an enchilada now, man. It's lunchtime.
Well, it is actually, but
well, again, I want to get back to what I was saying at the very beginning about the fact that we think the universe is flat, and yet we can only explain 30% of the density.
Yeah.
Well, so people started working out, if we have this uniform, whatever you want to think of it, negative pressure, anti-gravity, whatever, throughout the universe, it's just uniform throughout the universe, how much energy per volume would it have? And we can convert that energy per volume to a mass per volume because of a little equation called E equals mc squared.
That we've heard of.
Einstein. And so you figure out the mass equivalent to the energy density that you need for dark energy. It's 70% of the mass energy density of the universe.
There's the math. Okay.
And so it solved a big problem. That missing 70%, now we give it a name. It's dark energy. But it created a new problem because we didn't know that it was supposed to be there because we were expecting a deceleration.
Yeah.
So now we've solved the missing 70%, but we've created a new problem of what the heck is this stuff? And how does it work?
So you've established that it exists, and you can prove that mathematically, but you don't know what it
We don't know
is.
how it operates. We don't know what it is.
So what you're saying between this week and last week
Mhm.
is that the vast majority of the universe, we don't understand at all.
Right.
We know there's stuff out there, but we don't know what it is. We don't know what it looks like. We don't know anything.
Every atom, every person, every planet, every star, every galaxy, every black hole in the whole universe, 5% of the universe.
I feel so insignificant.
Yeah. Okay, so let's go to dark energy for a second before we have to take our next break in a little bit more than a minute. I'm not even sure what.
Yeah, you don't even have the words. I could see it forming in your mouth, and then it just kind of hung up.
It just sort of died right
It
there.
just kind of fell out of your skull and hit the table.
Here's the question that we always ask our students when they discover something. So what?
Well,
so what? That dark energy exists and the universe is expanding. What does
Right.
that mean?
well,
Why should we care?
that's an excellent question because as a science person, that's something I get asked, more than once. Is why
Try being a historian.
why are you studying this stuff? Who cares?
Yeah. who cares?
But the better we understand the universe, the better we understand reality. The better we can understand everything. So things like cell phones and GPS rely on general relativity that you wouldn't have thought had a practical application back when it was first invented.
Okay,
All right.
you just brought in general relativity, and we hadn't talked about that before, had we?
Well, that'll
E
give us
equals
something to talk
MC2.
about. Yeah.
Yeah,
MC
well,
squared. Okay.
We're going to talk
that's where
about
that's
that.
where that came from. But that
Well,
idea.
Talk about that after the break.
When you support McWhinney History Education Group, you also support the many young workers who operate and maintain the company's digital operations. These are dedicated university students who handle many things such as filming, recording, and editing content for McWhinney, as well as cultivate the layout and structure of McWhinney's various websites, including its associated channel on YouTube. We are a nonprofit organization that exists from donations from interested persons and history enthusiasts alike. Donations enable our students to obtain a higher education, job training, and career bolstering skills. If you would like to donate, please visit us at www.mcwhinney.org and click on our About Us tab to learn more. Bear Leader Tours. Where will Bear Leader Tours take you? Everywhere. Paris, Bruges, Trieste, battlefields, Pearl Harbor, Pacific beaches, New Orleans. Join the adventure. www.mcwhinney.org.
Welcome to State House Press, a nonprofit publisher of quality books. State House Press and the McWhinney Foundation Press are part of the Texas A&M University Press Consortium, which handles retail distribution for several small but distinguished publishers. Our entire list of offerings, with pictures, summaries, prices, and easy online ordering, is available in our section of the consortium website. State House Press is proud of its reputation for high standards of scholarship and readability. In addition to this, we at State House Press have recruited the talents of individuals such as Phil Collins on his book, The Alamo and Beyond. We release not only texana by contemporary authors, but reprints of classic accounts of Texas life and history otherwise inaccessible to the public. Our book list also incorporates the publications of the McWhinney Foundation Press, specializing in the history of the Old South and the Civil War. We strive with our titles to make history accessible to as many readers as possible. To accomplish this task, we have recruited some of America's leading historians, as well as bright new scholars. We believe firmly in narrative history, in telling a good story, and in telling it well, without losing sight of the people who've made history and the events that changed a nation.
For questions or business inquiries, please visit the Texas Book Consortium at www.tamupress.com.
And we're back, and this is Paul Fabrizio.
I'm Don Frazier, I think.
Well, it all depends
I don't know where I am at this point.
Well, what we've discovered is that we're all totally insignificant.
Oh, yeah, absolutely
The
insignificant.
total mass, energy, whatever of the universe, no, not energy, but the total mass of the universe, you said,
All the
is-
normal matters.
all the
5%.
normal matters is 5% of the universe, and 60 to 70%, we don't know what it is,
Right.
but the universe is expanding.
We didn't think it was supposed to.
Well, no, we knew it was expanding, but we didn't think it was supposed to accelerate.
Okay.
It's expanding and
And
accelerating.
accelerating, yeah.
And can we see to the edge of the universe?
No, we can only see to the cosmic microwave background radiation. You can think of that as the point in history when the universe became transparent. The very early universe would be like the inside of a star. It would have been opaque and light wouldn't be able to travel very far through it. But at some point that we actually have a name for, we call it recombination, which is when the whole universe went from being ionized particles to the whole universe became neutral particles for the most part, which I think is actually funny how it's misnamed. It's called recombination.
Yeah.
That would actually have been the first time that those atoms combined into neutral atoms, so it should be called combination, but I didn't name it.
Yeah.
So at that time of recombination, which was a few million years into the age of the universe or so, then the universe basically became transparent. And so when we look far away in the universe, we're actually looking, in a sense, back in time. You've probably heard that before.
Sure.
Because of the speed of light. And so the farther away we look, the further back in time we're seeing the universe. So once we get to the point of recombination, after that, the universe is opaque. And so you can't see any farther. And so what we see there is just a uniform glow of the whole sky that's very, very low energy photons. It's microwaves. So we call it the cosmic microwave background radiation. It's coming from all directions.
But we can see back to that.
We can see
point.
back to there, but we can't see past there, and we don't think we'll ever be able to see past there because the universe wasn't transparent earlier than that point.
And how far back is that?
13.7 billion years.
That's a long time ago.
Yeah.
Yeah.
Makes my age insignificant.
Yeah, I mean, Dr. Wayne Keith has essentially given me low self-esteem.
Okay, so
We need a psychologist on here to get my self-esteem back.
I mean, do you want to continue? Is there
Sure.
more ways to make us feel insignificant?
Insignificant.
Or is there something that's going to uplift us? We're not even sure what to ask.
Well,
to be
no,
honest.
well, we were talking about relativity.
Okay.
And general relativity, you said that might have predicted.
Yeah, in fact, Einstein's original general relativity equations, he actually had a term called the cosmological constant. And he put that term in his equations because at the time, this is, in the 19 teens or so, that everybody thought at the time that the universe was static, that the universe wasn't expanding or contracting, but it was staying about the same size.
And riding on the back of a turtle.
Probably.
Yeah.
And it basically existed forever. And so he added this basically this anti-gravity term to balance out so that the universe wouldn't collapse. Because if you just had a static universe, it would collapse under its own gravity.
Sure.
And so he had this sort of anti-gravity term called the cosmological constant to keep everything static. After Hubble published his papers saying that the universe was expanding, Einstein he got rid of that cosmological constant and actually referred to it as his greatest blunder, that he didn't predict that the universe should be expanding instead of contracting or staying the same. But now that we know it's accelerating, they've actually brought that term back.
Oh, really?
And they actually use the same symbol and the same name that Einstein used. It's called the cosmological constant. And that's one of the leading ideas for what dark energy actually is, or how it works, is it's Einstein's cosmological constant that he created and then got rid of after Hubble showed that the universe was expanding. But now that we know it's accelerating, we still need some kind of anti-gravity. So it's actually been brought back.
Oh, that's pretty cool. Good for him.
So if he'd still been around in 1997, he probably would have done yes.
He
Accelerated at last.
Yeah, I just didn't predict the other direction.
He didn't predict the acceleration of the universe.
He would have got his 3rd Nobel Prize.
He might have.
Wow.
By the way, I did look this up today. The guys who discovered the acceleration of the universe in 1997, they did get a Nobel Prize in physics in 2011.
Well, that makes perfect sense.
Well deserved.
So, yeah.
When is yours coming?
Not yet.
Not yet. Okay. You've got big questions to answer.
I got to answer some big questions first. Yeah.
All right. So the big question I have is, why does this matter?
Why does it matter? Because
I said matter.
It's good to understand the universe.
Okay.
And it could ultimately help us understand what's going to happen in the distant future. I don't know how practical that is to our everyday life, but just a matter of human curiosity. What's the universe going to be like in 1 trillion years from now? And this can help answer questions.
Now, do we only have one universe?
We don't know. The thing about the universe is, by definition, it's everything we can see and measure.
Because it's universal.
Because it's the universe. That's what universal means. It's the universe. So if there's other universes, kind of by definition, we can't see and measure them. And so the idea of the multiverse is really speculation. I wouldn't even call it a theory. It's speculation in order to answer a question. And the question being, why should our universe be so perfectly set up for us to exist? Because people realized when they started doing these computer models of the Big Bang and the development of the universe over time, that if you change the numbers for all the fundamental constants that we have learned about in physics, if you change the numbers just a little bit, then you don't get a universe that lasts for billions of years. You don't get a universe that clumps into galaxies and planets. You don't get a universe that has stars that create heavy elements that we're made out of, like carbon.
So you change something.
You change some of the numbers, and you don't get a universe that can have life.
Is this called the chaos theory?
It's maybe related to the chaos theory.
Okay.
But basically, it's the idea that sometimes it's called the Anthropic Principle, that the universe seems to be designed specifically for life to exist in the universe. And so there's basically 2 ways to explain that, both of which I would say are not provable by science. One is you have a multiverse, and so if you have an infinite number of universes, there's bound to be some in which life can exist.
Stick.
Yeah, where life can exist. And obviously, we are going to be in one of the ones where life can exist because we do exist. And so that's one solution to this problem of fine-tuning.
The odds.
Yeah, you play the odds. If it's an infinite number of universes, there's bound to be some where life can exist. Of course, the other
makes us feel very insignificant as well.
Well, so that would I would put that simply as you have to invoke an infinite number of unobservables, an infinite number of unobservable universes in order for us to be here.
Which really starts leaning into faith and not science.
The flip of that is you only have one universe, but it was designed specifically for us.
I said faith before I was supposed to.
See?
Which is, in essence, the argument for religion.
Yes. And
the existence of a creator.
And while I'm not going to try to prove it with science, it only invokes one unobservable instead of an infinite number. So
that narrows your odds.
So that's what I tell people. The atheist universe versus a theistic universe is, well, you have to solve this problem one way or the other. Are you going to invoke an infinite number of unobservables or a single unobservable? It's a matter of choice, because I would argue that you can't prove it either way.
And there's no point in having one with 3 unobservables or 7 or 9.
I'm not sure what the point of that
Yeah,
would be.
there's no point at all. It's either all or one.
Yeah, it's infinite or one.
But right now, science only says there's one universe.
There's one observable universe.
Right. There's no evidence that there's another observable universe.
Right, because if we could observe it, it would be part of our universe.
Okay. Okay, that makes
That's
sense.
right, because it would be universal.
Yeah.
It would be inside the
It would be
tent,
inside.
and therefore it's not a universe. It's a subset of our universe.
Okay, go ahead.
I'm actually one thing. This is I wanted to mention, even though it's not totally related, but just using the word universe. When they first discovered that the Milky Way wasn't the only galaxy, they hadn't termed the word galaxy yet. In fact, galaxy is synonymous with Milky Way. It basically means Milky Way in Greek or something. So the original word or phrase that they used to use when they first discovered there was other things like the Milky Way was island universes. They would say, we're an island universe, and Andromeda is an island universe. And that's a terrible name because universe means everything.
Yeah.
And so luckily that did not stick. And they decided to use the word galaxy, which again was originally synonymous with Milky Way, and just apply that as a generic term for all of these things, all of these big collections of stars, and called them all galaxies. And we're the Milky Way galaxy now. And the universe was reserved for everything, which I think was a good decision.
So if you say the Milky Way galaxy, you're being redundant.
You're basically saying the Milky Way, Milky Way.
So that's almost like Rio Grande River.
Kind of.
Yeah. It's the Rio Grande River.
That's very similar because you're saying it in two different languages.
Yeah, correct. Okay.
Okay, so just to sum up, because we've got to take a break, there is no evidence, no observable data that there's anything beyond this universe.
And there can't be observable
And there
data.
can't be by the definition that we're using.
Right. That would be my argument. I don't know if everybody in the world would agree with me, but
that's where
that's where we are right now. Yeah.
That's what's on the test.
That's what's going to be on the test.
Okay, so study hard, everybody.
Yeah.
Try to make sense of this. Okay, we got 15 seconds left. I'm sort of speechless here. I don't know about you.
Well, but dark energy is energetic. All right, we're going to take this break.
We're going to think.
History has become one of the most fought-over battlegrounds in terms of shifting people's views and opinions about their country. In response to this, we have decided to launch a website called Go To History that will become your home for clear-eyed history content. Our objective is to put history out there, free of agendas, and allow you, the viewers, to decide what you believe and decide how to interpret this information. With experienced professors such as Dr. Don Frazier and Dr. Stephen Hardin teaching courses and creating agenda-free content for students and just plain history enthusiasts, the content of Go To History is vastly informative and unbiased.
History people, it's Phil Collins here. I am just giving a shout out to a couple of guys that you're going to be hearing from. And they're good friends of mine, but they're also incredibly knowledgeable historians. Dr. Donald Frazier and Dr. Stephen Hardin. Both great friends of mine, both helped me out with my book on the Alamo. And two guys, if you don't know much about history, these are the first two guys you should go to. Okay, what they don't know isn't worth knowing. Don Frazier, Steve Hardin, I hope you enjoy their presentations.
My name is Evan Williams, a history major at McMurray University, and I love the layout of the Go To website. I mean, it is singularly built from the ground up with user convenience in mind. Every study available is within a single courses tab, with each lesson having a single page for each of its individual videos, text, visuals, and quizzes, all at easy grasp. This is most definitely history made simple.
Please log on to www.gotohistory.com. This portion of the show is reserved for advertisements. If you are interested in filling this portion with ads for your business, please call 325-793-4686 or email director@tfhcc.com.
And we're back, and this is Paul Fabrizio.
I'm Don Frazier, and this is Wayne Keith.
We're all at McMurray University, and Don and I are sort of befuddled here. So, Don has an idea.
Well, no, the question becomes then, all right, if you can, you either have to believe in infinite universes, infinite unmeasurables,
Right.
or one unmeasurable,
Right.
which then starts to hit that boundary between faith and science.
You can, yeah.
Then that begs the question, if this is a universe that in which it was just kind of intelligently designed for life to exist. Is there life elsewhere?
Are
in the
we
universe?
alone?
Dun,
Yeah,
dun,
well, that's
dun.
obviously a big question that NASA would love to have the answer to. Every time people talk about, NASA's covering up evidence of alien life, I think they would be shouting that from the rooftops. If they ever discovered life on Mars or life in Europa or any place else in the universe, they found life, they would be shouting it from the rooftops because that means more money, right? To study that stuff. I assume that's what they would
That's
think.
a crass political.
Well,
way
yeah, I was
to
about to
look at
say,
it.
wow, now he's into your realm, man. Well, and I'm wondering.
I'm just saying that
We've got
there's
life,
no
give us
reason
money.
for them to hide it.
Well,
Right.
when I see all the stuff about, well, we're almost certain that we're going to find life underneath this polar ice cap in Mars, or in this
Mhm.
trickling down water, it's almost like they are leading the witness
Right.
with that sort of process. And I always have this sort of sneaky suspicion with all of their different activities and their experiments and their explorations. It's almost like we know the answer to this, but we haven't seen the evidence of it. It's almost like somebody slid it on a piece of paper across the table, said, open that envelope, and your mind will bam. And so now they're going, well, we've been told it's there. Now we got to find it.
Well, one thing that's been guiding the exploration of Mars for a number of years is the idea of follow the water.
Yeah.
And because every place we see life on Earth, there's water.
Even Antarctica.
Even
Yeah.
under the ice caps
Yeah.
and everywhere.
The thermal vents.
Most extreme places on the Earth where we can possibly see, where we ever see life on Earth, which there are some very extreme environments we do see life on Earth.
Yeah, my neighborhood.
There's always water. And so the idea is
Not
if
my
we can find past or present evidence of water on Mars, that's also a good place to look for evidence of life on Mars.
Sure. But I mean, to me, my impression as a historian, it's almost like they already arrived at that conclusion. They just don't have the footnote built, which is an interesting sort of conclusion to come to. It's like, well, they're hunting for it because they know it's there. They just haven't found it yet. But why do they know it's there?
That's the
They
question.
sort of
for you.
want it to be there.
Or do they
Is
just want it to be there?
So what's the answer to it? Do you just want life to be out there besides here?
I think that may be
Or-
part of it, but also once you start looking beyond the solar system, you start thinking about just how vast the universe is. I mean, the sun and our solar system is just one of hundreds of billions of planetary systems in the Milky Way, and there's hundreds of billions of galaxies just like the Milky Way.
You do the math, yeah.
Statistically, even if life forming on a planet was 1 in 10 trillion chance, it's happened many, many times.
Even in the Milky
Because
Way galaxy.
The universe
galaxy
is just
Milky Way.
that big, and so
The Rio Grande
you
River.
kind of end up with this weird situation where it's almost inevitable that life exists elsewhere in the universe because the universe is so vast. But our likelihood of finding it and contacting it is very small for the exact same reason. The
Because
universe
it's
is
so
so
doggone
vast.
big. So I'm wondering, maybe sometime in the past there was a note in a bottle that fell from space.
Hi, we're here.
it said, look over in this particular region, you'll see life.
And we just
Or-
haven't found that note.
or were they
we
uncorked
can't
it?
decipher
No,
it.
they found the note. The note was found at Roswell or something like that. But they opened it up and it said,
What are
what
your
makes you so
footnotes?"
special?
Do you really believe there'll be life someplace else?
That we're going to find it.
Yeah.
I hope so. And in fact, the way that I suspect that we will discover life elsewhere in the universe is not the way that would make for a good sci-fi movie. I'm sorry to say. My prediction. So
Okay.
I'm predicting
Here we
this.
go.
Wow.
And so
It's on
this is
tape.
true. We can look this up later. My prediction is that the way we will discover life exists elsewhere in the universe is we will discover free oxygen in the planetary atmosphere of another planet around another star. Which is not exactly. That's
Okay.
It's not the makings of
Free oxygen as opposed to
It turns out that
cash oxygen? What are we talking about?
Credit oxygen.
O2 in the atmosphere. You guys know that there's like 20%
Right.
O2 in our
Yeah.
air, right?
Right.
Okay. Well,
Unless I'm diving.
We
And
know
then
where
we
that-
up it up to 30%.
we know where that comes from, right?
Yeah.
It comes from plants. if before there was plants on the Earth, there was no
Oxygen.
large amounts of oxygen in our atmosphere. Oxygen is nasty stuff. It's highly reactive. Ask a chemist, right? Oxidation is
called rust.
Exactly. And so oxygen wants to react with things. And so it doesn't stay in just O2 in large amounts in a planetary atmosphere unless some process is actively making it. The only process we know of that can make enough to get that much oxygen in our atmosphere is plant life.
Expiration.
So if we see a large amount of free oxygen, like 10, 20% or whatever, in the atmosphere of another planet, that would be really strong evidence that there's plant life, at least, on that planet.
So you're
saying, there is a possibility we can be able to do that in the next few years.
So you're saying that it's plant life that is the key to... I mean,
Our
plant life is life.
Yeah, plant life had to exist before animal life because you had to have the free oxygen in order for us to be able to breathe it. And so if you look at the history of the composition of the Earth's atmosphere, the first billion years or so, or a couple of billion years, there wasn't a lot of free oxygen in the atmosphere. And there wasn't any animals either.
A lot of carbon.
There was little single-celled organisms in the ocean, and that was it. So it wasn't until...
And they were metabolizing carbon into oxygen, ultimately.
So, yeah, I mean, I'm not a biologist, so I don't want to get into the details, but it wasn't until... billion and a half years ago, about halfway through the Earth's history, that you get this really big rise in the free oxygen in the atmosphere. And after that, you get things like the Cambrian explosion, where you have about a half a billion years ago, you have all these different kinds of animals, just about every body type that exists today, vertebrates, invertebrates, all different kind of stuff.
Roly-polies.
Yeah, they all have their origin in the Cambrian explosion, which of course wasn't a literal explosion. It was an explosion of diversity of life. And then it was even after that plant and animal life started colonizing land. Up to that point, it was still all in the oceans.
But what if there's some sort of life form that's
different,
exhaling not oxygen,
well, that's
exhaling methane?
That's the thing
is it life?
We don't know. That's the big question is, how do you define life? It's really hard to come up with a definition for life that isn't specific to Earth life. How do you make a definition that's completely generic and yet still have it include things from humans all the way down to little single-celled organisms, and yet be generic enough that it could apply to some completely alien thing that doesn't metabolize anything that we know of.
Okay. So essentially, we're a long way away from the bar scene in Star Wars.
Pretty much.
All right. Class dismissed.